Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be taking a look at this Zenith ZT1 terminal. From the best of my understanding, this is an all-in-one terminal that has a built-in 300 baud modem, NTSC video output, and a very nice Alps SKCC keyboard. This machine, unfortunately, has a fault, so we're not just going to be looking at it, we're going to be trying to repair it. And even though I have the original box and the original manuals, I don't have any service documentation for the computer. And it looks like whoever had this thing before had already taken it apart. The lid is removed and the screws are on the inside, but the thing looks absolutely brand new. So I don't think this thing's ever been used, and I guess it just never worked properly. So in this video, let's take a closer look at this terminal, see what it's all about, and see if I can get it working. So without further ado, let's get right to it. Until this was given to me, I'd never actually heard of the Zenith ZT1. Now, Zenith Data Systems, they made a whole bunch of stuff, including monitors, which I have featured on the channel, but also a whole line of computers, including an IBM PC, some terminals, and even CP/M-based systems. On the back side of the terminal, we have a video output, just NTSC standard, parallel printer interface. The power supply input says 31 volts AC, 10 volts AC, 12 watts max. Warning, this surface is warm to the touch, so probably a voltage regulator is attached there. We have phone connections for both the wall and the phone, so this is a pass-through. As far as I'm aware, this is just a 300 baud modem in the side of here. There's no RS-232, which is a shame because it'd be kind of cool to use this thing as a regular serial terminal, if possible. On the bottom side, we have some compliance stickers, and this is a ZTX-1-A. It's a sub-variant as far as I'm aware. There doesn't appear to be a single scratch anywhere on this thing. It definitely looks like this was never used. The keyboard, every single key has a nice matte texture, nothing shiny at all. Of course, these are very high quality keys. Quotation mark is next to the return key, which is pretty normal, what we're used to these days. The arrow keys left and right down here on the bottom row, up and down, and a small backspace key. Generally, the layout is pretty normal, except for, I guess, the control and the escape key. Again, the feel, absolutely amazing, and has a nice ping sound to it, which is the Alps SKCC key switch. These are the same linear key switches that are on the original Mac keyboards, Mac 128, 512, and plus a bunch of other computers from around that time use similar switches, and they feel amazing. And because this thing was in a bag in its original box, there isn't even any dirt on this, so this is as nice as it would have felt when it was new. As I mentioned in the intro, the lid was already removed, and someone was very nice to actually tape the screws in here, all 4 of them. And the keyboard is already loose. Seems like it's held on with some terrible ribbon cables, but they don't look like they're corroded at all, so that's kind of nice. I don't know exactly what fault this machine has, but I did hear that when you plug it into the power supply, I think some smoke was let out. So that potentially means maybe we have a bad tantalum or some other power regulation has gone seriously wrong. Now, one thing that I think is a bit strange is that these cables for the keyboard are crossed over. So they come out of the keyboard PCB and the left one goes onto the right connector and vice versa. Is that possible that that's correct? Just in case this is right, I'm going to write left on this one and R on that one, because I'm going to have to disconnect these obviously, and if this is right, we want to get this back in the correct way. Looking at the underside of the keyboard, there's a little bit of cardstock that's attached there, and the PCB is made by Alps themselves, which is very typical, and it's very nicely made with a thick back plate, good weight to it, and that's one of the reasons why this thing feels so nice to type on. On the left side, we obviously have the modem, and the right side, we have the digital electronics plus the power supply. On the bottom of the edge, it says Heath 1981, and Heath Kit, which is almost certainly what that's talking about, might have actually designed this, and Zenith sold it under their own brand, and maybe Heathkit sold a version that was a kit that you could assemble yourself for people who wanted to pay less. Looking at this system, we have an 8031, which I'm quite sure that would be a microcontroller that runs the whole show. We have an 8575 that will be certainly used for digital I/O, I suppose. Some SRAM 6116. We have 2 more SRAMs here, 2 114s, EPROMs, so 3 EPROMs, probably one's a character generator, the other is ROMs for the system. Everything else appears to be Jelly Bean logic, just 74 LSTTL stuff. Very easy to replace if any of them are bad. The only problem is sometimes the microcontroller can have mask ROM programming inside of it. The fact that the ROMs are external here probably tells us that this doesn't have any mask ROM inside. We have to look up the exact part number of the 8031-3 to see which version it is. But that could pose a problem if that chip is damaged somehow. Do have a speaker up in the top corner. Obviously this large capacitor there for the power supply. I can see rectification diodes there. And my assumption is, yep, there's a voltage regulator. It's attached to the back plate, hence that sticker about it getting warm. And generally everything inside here looks very clean. I don't see any obvious damage. Maybe the bridge rectifiers, there's a bit of brown around them. That could be flux, or they could be shorted. This is the power supply that was in the box. Zenith Data Systems, relatively chunky affair, a two-prong with a thing to screw it into your wall so it doesn't pull out. There's just an address and a part number 541006. It doesn't even have the output voltages on here, but it has the 9-pin connector that almost certainly is the one that goes with this computer. And I thought I had the part number on here, but it just says use approved power supply only, see manual. Well, it told us to see the manual, so let's jump to the manual. So apparently, the ZT1 is a personal information terminal. And really, because of that 300 baud built-in modem, it would allow you to get online without having to buy a whole computer and a modem and all the stuff that goes with it. You could just have something that very simply allowed you to dial up to BBS's, CompuServe, or whatever, do what you need to do, turn it off. Your Zenith ZT1 personal information terminal will let you talk, quote unquote, with many devices over telephone lines. Built-in cues and prompts make it easy to communicate via this information terminal. Even a person without typing skills or computer training will find the ZT1 easy to use. This is a Zenith ZT1 hooked up to a monitor and a printer optionally with your power supply and of course into your telephone line so you can dial up to your internet, or BBS's I mean. Note the keyboard does not have an on-off switch. It is live whenever the power supply is connected between the AC outlet and the power socket of the rear panel. Although the rear of the panel of your keyboard may become quite warm to the touch after a period of operation, this is normal and presents no danger. Kind of sucks they didn't have a way to turn it off. I guess they just expected you to leave it on all the time, turn off your monitor, I suppose, and just use up whatever power this was going to use up just to have it running all the time. Seems kind of silly just not to have a power switch on the back. We can get a glimpse of the user interface. The main menu just appears to have a directory, so these would be the telephone numbers, and I guess this thing is auto dial, I assume, although maybe not. Oh, it says manual dial, so yeah, I'm assuming it's auto dial. It really does seem like there's not a lot to using this device. It seems like it's 80 columns by 24, and there it is, hooked up to the Zenith monitor. That's the exact one I've had on the channel before. Think of someone you would like to call to try out your new terminal. Type his or her number at the cursor and you will see the number as you enter it. Note, if you type a hyphen in the number, a 1-second pause will result when you dial this number. If you type a slash, a pause of up to 5.7 seconds will result. Up to, that's kind of odd. This pause feature will be explained later in the setup process. You will hear clicking sounds from your terminal as it dials the number. So pulse dialing, I guess it doesn't support tone dialing. Hold the telephone handset to your ear and you will also hear the dialing sounds, just as if you were dialing the number on your phone. In the setup section, looks like we have a clock and auto answer capability, full duplex, half duplex, X on, X off. I think the terminal emulation in this thing is VT52, DEC VT52. Pretty common and well used back in the day. So far, nothing particularly interesting or useful. Escape sequences, but that's probably just VT52, so normal. Using a printer. So if you want to interface a printer to your ZT1, well, there you go. Odd, it's a 40-pin connector, but a majority of those pins are not even connected. We just have the regular D0 through D7, data strobe, acknowledge, and ground signals. You can use your terminal as an electronic typewriter. Looks like we have an Epson FX80 or RX80 printer attached. I actually have one of those printers. I love it, it's a workhorse. You can type a full page of text, edit and correct it, and then output to the printer, or you can type out dynamically. So I guess as you type one line at a time, it just prints it. And well, actually, that is it. It doesn't even talk about what power supply we should be using, like if this is the right one or not. I mean, it certainly looks like the same power supply, but nowhere in here does it talk about the actual part number. Now, besides the manual, we have a personal information quick reference card, but this just talks about the escape codes and some of the functions. And there is an addendum for the ZT1A, and this said ZTX1A inside on the sticker, but this thing appears to be just a ZT1A. Looks like they've added some password capabilities to the firmware. for TimeNet, Telenet, Source, which must be another online service. And this is the source enhancements for the terminal, whatever source is. Well, that's pretty much it for documentation. I can't find anything else. We're on our own for trying to figure out what exactly is going on with this thing. All right, first things first, I need to check for shorts. So I'm going to check those tantalums and these diodes. And then I suppose I can check these two capacitors. It could be simply that this cap needs to be reformed, so it's kind of shorted right now. And once it's reformed, everything will be just fine. But the fact that screws were removed from this kind of leads me to believe that whatever's wrong with this thing was wrong with it years ago, and that's why someone took the screws out and left it unscrewed in the box. We're going to use the multimeter set to continuity mode just so we can beep out these diodes, see if any of those are shorted, or these capacitors as well. Actually, I've just switched to diode test mode. Let's take a look at these diodes. So when you're testing these in this mode, the black probe goes towards the band. And 0.58, that looks good. That's exactly what we want to see. We don't want to see any of these shorted or open. Shorted would cause all sorts of unhappy things to happen in the power supply. So that one is good. You do have to poke through any kind of flux, which I think is what this brown stuff is that's on here. These were probably hand soldered onto the board at some point. Okay, all four of the diodes are looking good. This is a battery. I thought this was a capacitor originally, but this is probably a NiCad battery, and I can see corrosion down on the bottom of the case. So let's cut this out. Let's see what the damage is underneath. Oh, I can see some damage. Was that really a 1979 date code for this battery? Or no, right there, 1982. I wonder, that must be some other code. So 1982, 18th week. Yeah, this is definitely a NiCad, and you can see some crap has leaked out of it. And yep, we definitely have a little bit of corrosion that happened here. Now, hopefully this is all to do with the charging circuit for this battery. So that transistor there, the diode, it's probably all somewhat related, I think. I think this leakage really just sort of went off the board down onto the bottom of the case, although we're gonna have to remove this PCB to really see the full extent of it. And unfortunately, this ribbon cable is not soldered. Okay, good. I thought this was actually soldered in. There's a strip on both sides that plugs into. Very nice touch there, Zenith. Okay, now back to the power supply. So we know the diodes are good. We have a 7805 there. And can we see the other one? We cannot. So let's get this capacitor out. We'll need to test this anyways. I think there's some double-sided adhesive holding this onto this bracket. So that zip tie was just for extra strength. So I'll just take out the fasteners holding the bracket in, mainly because I wanted to take a look at that part there. So that has some kind of a custom part number on it, National Semiconductor. I wonder what that is though. So I'm just going to disconnect the capacitor so I can remove this from the board so we can take a closer look at this. And on this capacitor, the positive side is marked with these pluses. Although, since this thing is stuck to it, can't see what capacitance should be on here. Ah, there we go. Yep, double-sided adhesive. Okay, 10,000 microfarads, 15 volts DC from 1982. But let's hook it up to my LCR meter just to see. Now with this LCR meter, if you have it set to 1 kilohertz with these large value capacitors, if they're working, generally can't measure them properly. So you have to lower the frequency down to say 100 hertz. It's 11.5 MF, which is the same thing as 11,000 microfarads, and the ESR is 0.1, so that seems fine. What I'm going to do is try to reform this on my bench power supply. There are loads of videos out there on how to do that. I'll try to link one down below if you're unsure of that, but it just involves slowly bringing this thing back up to around 14, 13 volts, around the top value that it's rated for, but to do it very, very slowly. So I currently have it set for 4 milliamps, and it's just very slowly charging the capacitor, and I have it set currently for 8 volts. All right, it has already reached 8 volts, and it's drawing 0 milliamps right now, so I don't think this capacitor really needed to be reformed, or it kind of brute force reformed whenever this thing was last attempted to be powered up. So I'm going to lower the current available to 1 milliamp, and I raise the voltage up to 13 volts, and it's just very, very slowly charging this up all the way to 13 volts. Okay, while this reforms over there, let's just take a look at this again, and let's see if we can notice anything out of the ordinary. So we have the little bit of damage that was caused by the leaking battery. These are the connections for the capacitor. These little caps, I'm sure, are totally fine. Other than those two tantalums, let's just see if those are shorted. I'm going to have to grab another multimeter. in continuity mode. See if these are shorted or okay. That one is fine. Let's make sure that's still in continuity mode. It is. And that one is fine as well. It would have beeped if there was any kind of short. What about these little capacitors here? That's okay. That one's okay. I don't really see many other tantalums. There's a couple tiny ones here, but they're probably just fine. That's on the video output, very low voltage. That's a ceramic disc. I think these are fine. It's part of the crystal oscillator circuit. Definitely don't see any kind of leakage on these two caps. Just a little bit of flux residue. Yeah, I mean, everything seems fine here. Maybe there's more to be seen on the underside from the corrosion. Who knows? Maybe this corrosion like leaked onto the bottom side of the board. So perhaps it's worth just lifting this up to look at the other side. I really don't like unplugging these ribbon cables, so I am going to avoid that if I can. I think there's one more screw, yep, back here on the power input. I think the PCB is free. All right, well, luckily things look fine on the underside. This ceramic cap though, I wonder if that was shorting to the underside of the case. That might have been a problem right there. I'm going to put a little piece of capped on tape on that. In fact, I'll just put 2 pieces of capped on tape on there just to make sure that it's got a good coating of tape so it doesn't short out on the board anymore. This fake capped on tape I have is so junky because it's not very sticky. I really don't like it. I'm just warming up the desoldering iron. I'm just going to pop out the little connections there for the battery that I cut off. All right, there's one of the little leg offcuts, and there is the other one. Corrosion wasn't too bad, all things considered. Okay, and I'm just looking down at that capacitor, and that capacitor doesn't even touch the bottom plate. So there's no way that that was the short that was causing the potential smoke that this machine reportedly had when it was powered up. PCB is back in the board. I'm just going to check to make sure this component, whatever this is, isn't shorted. And it doesn't appear to be shorted. So whatever this is, just reverse the leads. There's just a little bit of a beep there, probably from a capacitor somewhere. So whatever this is, it's not shorted. 0.51 volts. I know you can't really read the multimeter that well, but it's a normal diode drop there, which is good, a normal diode drop there. So yeah, I'm going to say that whatever that is, could be a voltage regulator or something, that is fine. I'm not shorted as well. All right, well, that capacitor's been sitting here at 13 volts the whole time. So I'm going to unplug one of the legs from the power supply. Wow. And it's sitting there holding that voltage without any issues. So this Sprague cap is in good shape. I do need to discharge it before I hook it back up to the system. So let me find a resistor to do that with. So let's see, I think I have some discharge resistors right here. Look at that, still at 13 volts, amazing. There it goes. Don't know what size resistor this is, but it's large enough that it's not gonna overheat. Does it get warm? Oh yeah, it's a bit warm. That thing stored a lot of energy in that little silver cap. Not so little. It's not hot, but it's warm. Now, one thing about these types of caps, and this will be an interesting little test, is when I unplug one of the leads, the voltage should probably go back up. Let's just try that right now. Yep, look at that. It's self-charging. Is this like perpetual energy? No, it's not. I think it's just like extra electrons are still inside that thing. And when you drain it, you know, there's internal resistance. So some of them are hidden away where it can't be, well, they can't be drained super quickly and easily. So when you unplug it, they kind of migrate around, and that's why the voltage goes up again. So we'll just hook it back up. Now, one thing with this you should never do is hook up the power supply without that capacitor or some capacitor hooked up to those leads. And that's because almost certainly the AC volts that gets rectified and turned into DC is stored in this capacitor first before it goes to the voltage regulator or regulators. And you really need to get that hooked up just for stability of the entire regulation circuit. So for now, so we can run this thing with access to all of these components so I can measure if anything seems out of the ordinary, I'm going to hook this up with clip leads. And I'm going to reattach the fasteners for the 2 regulators, or one regulator or whatever the other one is, just so they're getting contact with the back plate. Running these regulators in free air when you have any kind of load on them is a recipe for damaging them. So we'll just double check. Okay, the red wire is going to here, which is where the pluses are. That's the positive side. So everything looks fine there. And this power supply, at least according to what we see on the back here, is just AC. So there's no DC in here. That means there's not really anything to fail. And I don't know the pinout of the connector, so there's no way for me to really test this thing. And of course, this has no power switch. I can't even plug it in before this whole thing is turned on. But I don't think it really matters because someone already tried to turn this on before. And if it was going to destroy this board because, say, this power supply is bad, that would have already happened. But we would have also seen visible signs of destruction, and that's not something we see. Before I connect that up, though, we are going to hook up the multimeter to the cap, just so we can measure its voltage once we power up the system. But keep your eyes peeled for any kind of smoke. Okay, 12 volts. I mean, that seems fine. And I heard the relays click, by the way. Now, I'm wondering if the smoke that came out of this was maybe the battery, because like the charging circuit is going to be trying to charge it. Well, the pads are completely gone. 1.7 volts to the battery? I suppose if that was a single NiCad cell, maybe that's an okay charging voltage, 1.7 volts. Yeah, I think it would be. Well, it's kind of going up on its own too. Anyways, let's check the voltage on one of these chips. So we're at 4.96 volts. That looks fine. So that means the voltage regulation is working. Yeah, this one over here, that one's quite warm. This one here, not so much. So I'm really glad I reconnected that because that could have damaged that pretty quickly if it was just in free air. Yeah, that's hot. All right, well, I think this thing might actually be running right now. So I'm gonna unplug the power supply. I hooked up a scope probe to the video output. I have this thing set for 1 volt per division. We're in multimeter, or sorry, scope mode. Let's plug this back in. So when I touch the middle pin, it just goes up to 850 millivolts. So we definitely don't have video output. No, we do not. I thought we would have a simple working system at this point, but we don't. There is nothing coming out of that. We're at 200 microseconds, but if I change the time base, 1 millisecond, 20 milliseconds, I mean, we'd be seeing stuff on there if there was an active video signal. So there 100% is not a video signal on there. This is what's really good about having a scope, is because we're able to like see what's going on. Let's just pick a random pin on this large IC here. Yeah, that looks normal. 5 volts, it's like, you know, I don't know what this signal is. We'd have to look up this part number. This is the microcontroller, I think. Let's pick another random pin. Yep, that looks normal, I guess. That could be like a flashing cursor for all we know. Who knows? Now, this system obviously generates its video using entirely TTL logic. I mean, we could have a problem just with a bad socket, right? With a bad connection in one of the sockets. So I'm just pulling the power supply out. Let's do the old push everything down. Now, a couple things. I haven't verified that we have a good reset circuit. I haven't verified we have a good clock signal. Thing is, we saw normal activity on this. That tells us that this is getting a good clock signal. If this clock were dead, then this chip wouldn't be outputting anything that would look normal. We wouldn't see sort of activity on it like we're getting. But the assumption I have here is that the 214s are the video buffer. This is the character ROM, and then the TTL logic just reads out the video buffer, accesses this, and then there will be a shift register that actually outputs the video signal directly to this, you know, with a few, like a transistor right there, maybe to level shift it. Okay, with those chips pushed down, let's plug this back in. Nope, no change. See, it just went up to 800 millivolts or 850 millivolts or so. Okay. All right, so this is where not having schematics for this sucks, because if I had the schematics, I don't think it would be difficult for me to just analyze that video output circuit and go backwards just to figure out where the signal is stopping, or like what's generating the video and why it's just sitting there at 850 millivolts. It's just stuck high all the time. We should be seeing sync signals. We should be seeing, you know, the actual ups and downs of the video signal itself, like the character data, but we're not. So I think the failure is probably somewhere late in the video stage. Whatever combines the sync signals, which will almost certainly be generated separately from the character data, there's probably a chip that combines that stuff, and that's not happening properly. Looking at the excellent Apple II book, the Apple II circuit description really explains how the Apple II video circuitry works, and the Apple II is probably relatively similar to this machine. And by similar, I mean it doesn't use any kind of video display processor like a 6845 or 6545 to help generate the video. It's doing it all through TTL logic. The main difference on the Apple II, of course, is that it is using main memory on the system to actually generate the video, so there's some interleaving going on there, while this appears to have the 214 chips to do that. But if you look at this, the 6502 can write to the screen memory, which is the main RAM in this case, and that data gets latched over to the video generator, which is some TTL circuitry that just outputs the actual video data. That's the character data itself. Now, part of that's not shown on this block diagram is there's going to be the character generator ROM, which on Apple II is a Signetic 6513, I think, or maybe on later ones it's a normal EEPROM. And that video data gets sent out to the transistor that then is actually outputting the video signal. But there's also the video address generator, and that's what the 6845 does on a lot of other systems, but this is TTL logic in this case. And that accesses all the memory, and it does it in a way that every 60 times a second is updated, and that latch data is what goes to the video generator. But the video address generator, besides accessing the RAM, also is generating the sync signals and the color burst. Now, in the Apple II, I forgot, this is just mixed together with some resistors, and that goes to the base of this transistor. I don't know if that's happening on this board, but maybe that is the same. But on the other hand, this might be using normal TTL logic to do that combination. Now, generally you want to use resistors because the sync signals actually can go beyond the video signal. So if you just use TTL logic to make the entire video signal, well, then that means that the sync signals aren't going to be at the correct levels, but a lot of monitors do just work. But we weren't even testing this on a monitor, right? We're using the oscilloscope so we could see that there was no video signal. Now, there's a couple different ways we can try to approach this troubleshooting session. One thing is we can look for the shift register, which there almost certainly is. That's going to take the parallel data that's coming out of the character generator and outputting a serial string of data, and that is what gets sent to the video signal. The Apple II uses such an IC. And that's what you see on this block diagram. There are actually two shift registers, one for text mode on the Apple II and one for graphics mode. This doesn't have graphics mode, so it's just going to have one. And on the Apple II, that goes through this data selector, but that's not even necessary on this system because the data selector will switch between, the different graphics modes, like these two different streams, low-res video, high-res video, or text data. So on this design, we have to just imagine that there's a shift register that probably goes directly to the transistor through a resistor, or it's going through some TTL logic to combine it with a sync, and there's no color burst because this is a monochrome system. So it's really just a sync signal and then the text data, which actually is coming from up here, but whatever, it's all the same here. But what we need to do is take a look to see if we can find on this board those shift registers so we can actually look to see if we see that pixel data flowing through them. Oh, and I'm sorry, I got it a little bit wrong. I think 2513 is the character generator on the Apple II. And you notice it has D1 through D5 as output. So it has 5 outputs. And the input is what comes from RAM. And that goes into this. And the reason why it has 5 outputs that are used, it might have more outputs that just aren't used, is that each character on the Apple II is made out of 5 pixels by 7 down. Well, the scan line is going across the CRT, and it's only generating one line of pixels at a time, right, for building up the characters, and that's why only 5 outputs are used. So that is going to be similar on this again. And the 74166 is a shift register, 8-bit shift register, so that is what's generating the text mode video data that comes out of QH, and it goes down to this data selector. And I'm pretty sure that these chips, LS194s, are 4-bit shift registers used to do the graphics modes. Now, the whole circuit's kind of elegant, but also a little bit more complicated because, of course, it has a bit more capabilities with graphics mode and low-res graphics mode, stuff like that. But anyways, in the end, video data comes out. So I'm going to look at this board to see if I can figure out which chips might be relevant here, and so we can start poking around. Okay, right off the bat, here's the 166. This is the 8-bit shift register, and notice it has some traces that go over to the EEPROM, which is almost certainly the character ROM. So we need to take a look to see if we have character outputs on this chip, because if we don't, then we know the problem is more upstream. So that's just a good place to start. We got to start somewhere. Normally, I have some schematics showing up on the lower section below the oscilloscope there, but we don't in this case. And first, we'll just check the output of the video signal, and yep, we're getting that 798 millivolts. And now we're looking at the output of that shift register, and there is nothing happening on there. Right, okay, so we know the problem is probably further upstream. Let's take a look at the character generator ROM, which is a 2516. So the data lines are 9, 10, 11, and 13 through 17, but the address lines are the important part. That's what's going to be going into this chip to select the pixels that are coming out of it. So for sure, pin 7 should have some activity on it. And when we look at that, absolutely nothing is happening on pin 7. It changes a little bit when I touch it, so we know there's some life, but that's it. Let's just check the voltages real quick. Make sure we actually have a good voltage VCC pin 24. Okay, we're getting 5.04 volts, so that's good. But the inputs to this chip have nothing happening on them. So clearly there's no way we could have any characters coming out of this without any activity on the character ROM. Oh, there's a little bit there. Okay, let's go through all the pins. Okay, wait a second. Seems like nothing's happening. If I push down on it hard, nope. Well, whatever was there is gone. I was on pin 3, I think. What the heck? Let's just go on this pin, and I'm going to push on parts of the board. I mean, you saw there was some activity there, but it was weird. It was all at the top, which clearly is not going to work. Well, whatever was there is totally gone now. I do have to wonder what's driving these data lines, or their address lines, but it's coming from the RAM. So these are effectively data lines, and the RAM chips are right here where my finger is. Why does it come and go? Let's power cycle the computer. Unplug it, plug it back in. Let's see if we get... My assumption is something is trying to drive these address lines on the character ROM. A bunch of them are just stuck low. And then there's that one. Let's just move the ground lead. No, that's fine. No, we're fine. Just for a hunch here, I'm going to remove the character ROM. The chip's not warm or anything like that, but what if it's bad and pulling those lines up to 5 volts? It's possible. Okay, let's check out one of these lines now. Oh no, it looks exactly the same. Okay. So we know that is not the problem. But where are those signals coming from? And you know what? What was there with those blips? Gone. Okay, so these are the outputs from the chip, and they're at 1.5 volts. But that's normal because the EEPROM should be driving those signals. We're down on the data lines. Over here will be the same. So let's poke around on these SRAM chips. These are the video RAM chips, I presume. 2114s, very typically used for video RAM. So these chips have 4 bits for output. That's 14 through 11. And then the rest are address lines and a chip select line. Let's see if we see activity on the output of these chips. Okay, that's 11. That's a no. 12, 13, and 14. We're seeing nothing. What about the other one next door to it? Nope. No, this one also has no output. Let's check chip select. That is low. It's active low, so that's normal. And the other one? Same. They're probably hooked up together anyways. And then we have the right enable line. Oh, so there's stuff being attempted to be written to these, and it could be like the flashing cursor or anything like that. And in fact, if we power cycle this machine, we should see a burst of more activity. So I turned it off. Okay, maybe not, but there are little changes here and there. Okay, so I'm going to poke around the address lines, and only one of them has activity on it. I think this is address line 8. Looks normal, but oh, and so is that one 7? Oh, sorry, the first one was 7. Now we're on 8. That looks fine, but then 9 is just stuck. And then here we're on address line 2. Got nothing. 1, 0, 3, 4, 5. I think that is, actually that one was 5. That one was 6. So really not much happening on any of the address lines. Now I'm sure all the lines are parallel between these 2 chips. Yeah, they look the same. So we should have a little bit of activity over here. So that's nothing, that's the same. And then yeah, we have that. So stuff is going on with this machine, but it's weird. And I still think the problem is maybe upstream. Okay, so far I've ruled out that the EEPROM is the problem. I mean, it might be bad, but I doubt it. I think the problem is upstream from that. And the shift register, I mean, again, it's not going to do anything if there's a problem upstream. So that would be why we have no video data. The 2 video RAM chips, the SRAM chips, they seem to be kind of not doing much either. And only a few of the address lines actually have any activity, and none of the output lines have any activity. Oh, and we saw the right enable line getting pulsed as well. Now, for all I know, the code that's running on the CPU, well, the MCU in this case, maybe it's using the 8575, which I'm pretty sure is like a parallel IO type chip. Maybe some of the outputs on this are actually generating or driving the video circuitry. I mean, who knows how this is all hooked up. The fact that it's sitting right here maybe implies that it's somehow related. But again, without schematics, it's not the easiest for us to know exactly if that's the case. 2845 might hook this part of the circuitry up to the CPU side. The computer just made a click noise on its own. That doesn't make any sense. Why? Oh, you know what? It looks like it's dead. Yeah, it looks like we have no longer any activity anywhere. Do we still have 5 volts? No. The whole thing is running at 800 millivolts right now. Why? What happened here? Okay, I hooked up the multimeter back up to the capacitor, which is definitely connected to the board. Let's see what we get when we plug the power supply in. Nothing. Everything looks fine. I mean, it was running, right? We saw it running. We had smooth or good 5 volts. But we're getting absolutely nothing DC volts out of the power supply. I think the power supply might have died. This brick here. And you can see there's no fuse or anything on this whole system. All right, I'm gonna set this to AC volts. And we're gonna poke around on the board here. I don't know where the other trace, I see 2 thick traces coming from the connector that go to the bridge rectifiers. Okay, we're getting 0.22. I'm pretty sure that is the AC input that's going into the bridge rectifier. I think it's bit the bucket. I think that external brick has died. And that just took out the main power supply. Now, this is not the same problem we've been troubleshooting. It's unrelated. I'm positive this is unrelated. So I think what I'm gonna do, I'm just gonna feed 12 volts directly into this cap from my bench power supply. And one of the issues I see with this is I think this power supply is sort of like a dual voltage thing. There are no screws in it. And I think part of the AC volts probably are for the modem. And then the other part is just for the digital board that gets converted down to 5 volts just to run the whole system. Okay, so that's the bench power supply. Let's turn this on, and I'm gonna feed this exactly 12 volts because that's what we saw on that cap. I'm gonna give it 500 milliamps first. Let's just see what happens. No, that went to current limiting. Oh, you know what? What if this thing has, what if something has shorted on here? I'm gonna try 1 amp. No, there's a short. There is a short across these wires. What happened here? I mean, my only assumption is that one of these voltage regulators has died. But when it was running, neither of them were even warm at all. Yeah, it's a dead short across that cap there. So I think the power supply, this AC power supply, was probably fine. It was just being pulled all the way down due to the dead short. I'm surprised the diodes didn't get damaged. Well, let's check these diodes for shorts, because if any of them are shorted, it would have this effect. No, those seem fine. Yeah, there's a short across that tantalum there. Well, it could well be that these tantalums are the issue, because we know those are very prone to going short. Yeah, that one seems fine, but this one has a short 0.6 ohms. Let's see on this regulator, 0.28. And this one over here, 0.21. Are you able to see that? So I'm just looking for the lowest resistance. And the problem is, of course, you know, it's not an exact science. 0.21, 0.245, and the tant here, 0.28, so that's even higher. So I don't think it's the tantalum, and I don't think it's that. I think it's this one over here, and that's the one that we don't know what it is because it's not labeled. So to try to figure out what this is a 7805, but this one over here I don't know. So those pins are common. Those pins are common, and they're shorted. And the output, which I think is this pin on the right, that is not common. So let's see where this goes. Does this go to this chip here? Okay, so the 7805 goes to this TTL logic chip. But what does this output go to? I may have to take the board out again and figure out where it goes. Okay, that's the output. It goes to this little capacitor here. I wonder if it goes to like this printer interface card. Nope. I wonder if this is for like the logic on this modem card maybe. Let's see. Oh yeah, it's on that pin there. Well, the reality is I probably have to take this board out again, and we can try to see where this capacitor, this is the little bypass cap off this regulator, where it's going. And I can try to figure out what it goes to, and if it's just another 5-volt regulator or something else. Part number 207-442-54. I mean, that's not helpful. Incidentally, that is the one that was getting really warm while the system was running, but of course it wasn't burning hot. And because I had it attached on the back of the board here, it actually had some cooling for it. It wasn't like it was just flapping in the breeze, overheating. So I'm just going to spend a moment to remove that part from the board and confirm that that is what's causing the short. And while it's out, or the board's out, I can try to figure out where exactly that output goes to, like which chips. Maybe it's part of the board. Maybe it's the video circuitry has its own dedicated 5 volts for noise purposes. I mean, that's possible. But why isn't it just a normal 7805 like the other one? I couldn't tell you. And I have to hope that while this thing failed, it did not take out the AC power supply. That would suck. And yeah, incidentally, that's the output pin. It goes to that little bypass cap, and then it goes to a via right there, and where that goes, it's hard to tell. It kind of looks like it goes to a small capacitor right there, and then from there, I can't tell, it goes underneath chips. All right, there it is out of the board. let's see if we have lost our short. Oh, no, we did not lose our short. Still there. So there's nothing wrong with that regulator. Well, that's good because I didn't know what it was. So that pin goes to the bridge rectifier right here, but those diodes are fine. Yeah, I almost feel like I need to pump some current into this board using my bench power supply here and watch what heats up with the thermal camera. That could give us a quick indicator of what's going on. I also don't know if maybe the DC voltage makes its way over to the modem board and the short's over here. Yeah, there's the short also on this board. So definitely the voltage from the cap here makes its way directly over to the modem board. So I'm going to have to just unplug this because we need to isolate where the fault might be. Nope, still there. Okay, so the problem is not on the modem board, it's definitely on this board. I'm going to have some lunch and then we're going to inject some power into this and try to see what warms up exactly. All right, are we ready for a little heat testing to see what heats up as soon as I apply some current to this board? Let's see what's causing the short. It's got to be something up in this area. I mean, the tantalum, that, one of the diodes. I don't think there's much else. I have the modem unplugged. It's not going to any of the logic ICs, that's for sure. Okay, here we go. I'm going to turn this on. I'm not really seeing anything heat up. Okay, I am. Looks like it's that capacitor right there. Sorry for showing the screen, but the wire itself, the ground lead was heating up, oddly enough, quite hot, even though the positive lead was not. And then it certainly seemed like that little capacitor that was right next to it was heating up. Looking at the back of the board, that's the regulator I removed. This is the capacitor that I thought might be the culprit. That's next to the bridge rectifier. These are the connections that go to those two wires. So it was this one that was heating up quite dramatically. So I just lifted this capacitor off the board, and that's it. The short is gone. That capacitor freaking shorted. Oh, you know what? That looks like a tantalum cap, certainly, doesn't it? Yep. I'm used to them being yellow color, but the cylindrical shape on there, yep, it's a 15 volt. I'm just gonna replace this with a different type of cap. You know what's funny? With that cap removed, doesn't it look like there's a little bit of a burn mark on the PCB as well? That was probably the smoke that got let go from this thing that was reported to me when it was plugged in the first time. Okay, while I'm at it, I'm gonna remove and replace this tantalum as well. I just don't trust it. It's on the same voltage rail. It's parallel to that cap. This looks like it's a 2.2, maybe at 20 volts. So it's a little further away than the other one was, which was 15 volts. Oh, great. So I've put two electrolytic caps in there, 4.7 microfarad, 50 volts each. I've reinstalled the voltage regulator, which is obviously not faulty. Well, we're pretty much ready for testing. Those are the two components that I've removed. Okay, so the board's back in. The voltage regulators are reattached to the back plate. We do not have a short any longer, so that is good. You got to make sure you unplug the capacitor, though, when you do the short testing, because if the capacitor is plugged in and you check for shorts, it's going to look like a dead short because this is trying to charge up that capacitor, which obviously the little tiny current in the multimeter is not enough to do that. With the power supply reconnected here, let's plug the main brick in the wall. Oh no. There's absolutely nothing happening. So my assumption is that this has a fuse inside and it has blown. Now, of course, we can go back to what we were doing before and try to power this whole thing up using the bench power supply. I have the leads just sitting right here. Let's make sure it's currently off, and it is. So I have it set for 12 volts. Okay, we're at 400 millivolts right now for the whole board. And let's just probe one of these random ICs. Yep, 4.96 volts. So we're back in operation again, but this AC power supply did seem to have bit the bullet. There's got to be a fuse in this that went open when this thing got shorted, so I'm gonna have to crack this open, I guess. Let me turn off the power supply here. I want to see if this clicking happens on the relays. Yep. And then turn it back on. Yep. So we're getting the clicks here as we would expect, but let's just see. I'm sure magically that did not fix our problem here. Well, especially because the character ROM is removed, but that did not fix our problem. On the output side, okay, we're looking at the address lines on the character ROM, and they look pretty much the same. How about on our video RAM? Yep, that's how that was looking. Just a couple of them are actually doing anything. Most of them look like that. So we just get sort of small amounts of activity, except for these two lines, which actually seem to have some pulsing on them. So there's an LS245 right here. I have my finger on it, and I'm assuming this connects the CPU to the video RAM subsystem over here. And let's just take a look. So on one side of the chip, we see activity, and on the other side, nothing. Nothing at all. And taking a look at these two ROM chips at the data lines, they look the same with a little bit of that downward peak as the left side of the 245. So I would say that 245 I have my finger on is separating the ROMs and the CPU side from probably the video subsystem. In fact, with the multimeter in continuity mode, let's just check some of these lines over here to see these. There we go, that's connected there. Yeah, it's connected to that chip. So that confirms this LS245 is connecting the data bus lines on this side to the video RAM. And it's possible even this chip here. We should look up what that is exactly. 8275. Oh, I'll be darned. This is actually a video controller. I just assumed this was like a parallel interface thing or something like that. But people were screaming at their screen telling me, no, that's a video controller or CRT controller. What we need to take a look at are these data bus lines. This is how the CPU would communicate with it to read and write into the registers. We need to look to see if these are just hooked up to the video RAM chips and that LS245. Because the LS245 is never being told to turn on or it's bad. Then there's no way the video output would ever be controlled to do anything either. And almost certainly this chip here is generating the sync outputs. I wouldn't be surprised. So it takes a clock in. Let's just look. Yeah. Horizontal retrace, vertical retrace outputs. So it's generating the sync signals. It's not just TTL like on the Apple II. I was kind of wrong about all that. So we need to make sure that this thing actually has a clock signal going into it. But more importantly, we need to look to make sure that it's got some data bus activity, because if the CPU is not able to write to its registers, it's probably never going to start generating syncs. Not until the CPU is able to tell it to, hey, turn on. The data bus lines are over on this side. And let's just see if like this line here, which I think is 7, is attached to anything on this chip. Yep, there it is, right there. And 6, 5, yeah, okay, so they're all connected together. So the data lines to the RAM chips, the video RAM, and the CRT controller, along with possibly the SRAM down here as well, might also be separated out. Let's take a look. Oh, it's also there. So this SRAM chip, a 6116, the regular 214 video RAMs, and the CRT controller are all on the other side of this 245, and we don't see any activity whatsoever. That doesn't mean this chip is necessarily bad. We need to look at the select line or the direction signal just to see if this is actually being turned on, because this is probably being turned on by some other piece of logic around here. So our LS245 is not going to do anything unless the output enable is turned on. So this would have to be tied or brought low at some point, pin 19, and then direction signal. We got to look at the datasheet to see what this direction signal does, like which way is which. I can never remember. One direction is from A1 to B1, and if that signal is reversed, or it goes high or low, then it's B1 to A1, because this is a bidirectional bus transceiver. And when output enable goes high, then the outputs on both sides are just high Z or high impedance. They float, basically. It's the same thing as the chip just being removed from the board entirely. So this is actually good. We're making some progress here, because without that LS245 working correctly or being instructed to work properly, there's no way that the CPU can read and write to the video RAM or the SRAM, which is probably needed for the system to even run. And of course, it can't read or write to the CRT-C, the CRT controller, to turn on the sync signals and program that chip. So I'm going to start on pin 1 here, and let's turn on the bench scope. Okay, well that's interesting. So it's high, and we should look at the data sheet to know exactly what that meant, but we see a pulse there, and we do see regular pulses, which would theoretically be where it's reversing the direction of this chip. Now let's take a look at pin 19, because that needs to be low. Oh. Well, that's very interesting. So we're getting normal activity on pin 19 as well. So whenever that signal is low, that's telling this chip to turn on. Now I'm going to hook up a second oscilloscope probe. Let's look at both those signals at the same time. All right, there are the two signals overlaid on top of each other, which is good. We wanted to make sure that the direction signal, which is the yellow trace, was also going low at the same time as output enable. Because if direction pin was doing something while output enable was not turned on or low, that's the red trace, then that would most likely indicate a fault. because there's no way that the direction pin would do anything if output enable was not asserted at all. So here's the interesting thing. I'm on the output enable pin. I'm going to reset the system, so I'm going to turn it off and on. Let's see if we see a flurry of activity. Oh, it was so quick and hard to tell. Doesn't really look like it, because you would think the first thing it would do is start reading and writing from the memory, like the SRAM chip that's there, and that doesn't seem to be the case. Yeah, I would kind of expect when you first power this up that we would get like a flurry of activity while it clears the video RAM and tries to write to the main 6116 SRAM. We're not really seeing that. Okay, so we're looking at output enable, and I just picked one of the random data lines. So I'm on, I think, pin, I don't know, 4 or 5. Okay, so here's what's happening. So when the red trace goes low, this chip should be turned on. And I'm thinking, based on the direction signal, which we haven't really looked at, it should copy what it sees right here, which this yellow trace, I don't know, is doing stuff, right? It should copy it to the other side. So I'm currently on pin 5, and that means pin 14 should have that on its output, I think. And it doesn't seem to have anything on the output. I am currently on pin 15, B4. So now I'm on pin 4, A3, and we can see that sometimes there's activity that should be copied over. And when I look at the other side, I am currently on pin 16, B3, which is the opposite side. Nothing. Nothing at all. So that sort of makes me think that this LS245 is bad, although they really rarely fail. I've had them fail, but it's not common. And without really looking at a full logic analyzer or maybe a 4-channel scope, so we can take a look at both the direction signal and the chip-enabled signal, plus a couple of the data lines all at the same time, I'm just going to swap that chip out. So we'll see if that makes any difference at all. Okay, the chip I just pulled out of there is a Motorola from 1981, and the chip I'm going to insert in is a Motorola from 1983. I'm not sure I've ever really had one of these go bad, but let's just see anyway. So I'm connected to one of the data lines that faces the CRT circuit. No, that made no difference. So that is our output enable signal, going low sometimes, and all the other lines are just doing nothing. All right, so this is the chip I just tried in the board and didn't make a difference. So I think the original chip is fine. Now what I want to make sure we don't have is something shorting the data lines on the CRT side. So all I need to do is just lift one of these pins. So I'll just bend it out slightly, just so I can probe that pin individually while the system is running, just to make sure that there's not something pulling that pin down to ground. I don't necessarily think there's a case. I think there's a logic problem with those 2 select lines, or the system's not really running code properly, so it's never even trying to read and write from this stuff. Although it's just odd that this does get turned on sometimes and the direction pin is toggled. You would kind of expect stuff to be happening here, but maybe there's chip select circuitry that turns this stuff on, and that's not working either. So we should probably check the chip select lines or output enable for that, RAS and CAS for these, which is probably generated by this chip, and the chip select line for this IC. But first, we are going to probe just this random line that's sticking out while I turn the system on. No, that made no difference. Okay. So the line sticking out does not have anything on it, while the line on the other side obviously has stuff on it. Yeah, it's just sitting there doing nothing. Same as all the other lines. All right, well, let's check pin 22 on the CRT controller. That is the chip select line. It's chip select low. What we could do is we can put this on normal mode so that we will only get anything updated on the screen of the scope. I'm going to power the system back on. We'll only see anything updated while that chip is being selected. And if we change this to falling trigger, then essentially what's going to happen is it's going to trigger when I turn off the power, which is right now, but it will only trigger when the signal goes up to 5 volts and then drops back down to turn that chip on, and there's nothing happening. So that chip is never being selected, which might explain why this is never being turned on properly to even talk to this stuff, because maybe the CPU, which I assume is this larger chip, isn't even running correctly. First things first, I just bent that pin back in for this bus transceiver. So we'll pop this back in the board. Okay, so let's see if we can take a look at the datasheet for the microcontroller, single chip microcontroller. We have an 8031. Now it's not an A and H, but I don't think that necessarily matters. Let's zoom in because I can't read this. 8031, it's got no built-in ROM, but it does have 128 bytes of built-in RAM. Okay, that's interesting. Oh, this is actually the automotive version. I'm assuming it's the same for the non-automotive version. Either way, port 1, 8-bit idirectional I/O port. So that's those first lines. Those can be used for anything, including chip select. And then we have port 2 down here, which seem to be address lines. Port 0 are also address lines, 0 through 7. Port 3, RxD, that's like, I guess, a built-in serial port of some kind. It could be that's what it's using to talk to the modem, actually. I suppose I should just do what I should have done all along. Maybe check the reset line is working and the clock crystal stuff is working correctly. And then we definitely need signals like ALE or address latch enable. That's just because the data line and address lines are multiplexed. So this gets toggled every time those switch states. I have clipped onto the CPU just for easy probing, just for making the video. So I'm on pin 9, which according to the data sheet is the reset line. Let's turn that on. We're looking at the red trace. To reset the system, the voltage should be high, so up around 5 volts, and then when it's idle, it should be down around ground. Okay, did you see that? It was high for a second and then went back to low. Let's just slow down the time base. Yep, there it is. There's our reset signal. It doesn't look super great, but I think that's good enough to reset this processor. Cool, reset's looking good. Okay, clock signal on pin 19. I just switched it to rising, and we are looking at around 6 megahertz, which my assumption is that's the correct speed for this system. Let's check the other crystal line. Yeah, that looks good enough. So we know voltage is good, reset is good, clocks are good. Let's check the ALE pin 30. All right, I think this is the ALA signal, which is address latch enable. I think that looks fine. And we have some extra functions on port number 3, like RD, external data memory read strobe and external data memory write strobe. I'm not super familiar with the way these Intel microcontroller works, but I'm assuming this is for reading and reading the ROMs and the RAM, and then writing to the RAM. So this is read, pin 17, and then that is pin 16. So this is the write strobe. Now the funny thing is, I thought that was the write signal we saw on the DRAM. Pin 10, write enable. Yeah, that pretty much looks the same, doesn't it? Like with the triple pulses. And maybe it's been buffered because it looks slightly different, like the waveform looks a little different, but essentially we're seeing those same 3 pulses making their way to the 2114s at least. And I can kind of assume that the write enable pin on the 6116, which is pin 21, probably going to look the same as well. Yes, it does look exactly the same. And why don't we check the write signal on the CRTC pin 10? Well, it looks exactly the same again. Nice how smooth it is. So it's definitely been buffered, but otherwise that is the same signal for sure, making its way from the CPU to the components that you would think would be written to, the video RAM, the system RAM, or whatever the other RAM is, and the CRTC. Okay, now I'm noticing here is a read signal on the 8275 on pin 9. I bet you that's that same read signal that comes right off the microcontroller. Yes, there it is. Looks identical. You see those pulses up there. And you know what? Looking at the direction pin on the LS245, that is the RD signal as well. Without a doubt, that is the RD signal. So that's on the CRTC. And here it is. Yep, there it is on the LS245. Oh, you know what? I just noticed something, everyone. On the LS245, pin 20, that's VCC. That's not correct. So I was looking at pin 19, which is that one, and then I accidentally clicked on pin 20, or touched it with a probe, and it's like 900 millivolts. What the heck is going on with that? So if we take a look at the VCC on the 214 SRAM, it's also low. Whoa, okay. Oh, you're onto something here. Let's just check another random chip. Wait a second, do we lose our voltage regulation? I mean, the power supply is running right now. What's happening here? Is this our problem? VCC, so that's, okay, so that's 5 volts on the CPU, and it's correct. Oh, wait a second. Okay, so this is the output of 7845. Looks perfect, 5 volts. And this is the output pin on the other regulator, the one that's unmarked, and that's also 5 volts, perfect. But I'm just picking random chips, and I know I measured this before, and they all look screwed up. What the heck is going on? What the heck is going on? Why would the CPU have 5 volts and these other components not? And I know I checked this before and we had 5 volts on these chips. Wait, that is the CRT controller and it's got 5 volts. I know, sorry, you can't see it. Let me click there. So 5.03, but if I go to the SRAM next to it, 900 millivolts. What is happening here? What is happening? You know, I don't have this motherboard fully screwed into the case. I just have one screw holding it in here just because I didn't want it to kind of slide around. Is it possible that these screws somehow ground the board and the ground plane is split or something weird like that? Okay, here we go. Let's try again. No. Okay, that made no difference. The problem is somewhere else. So what? There's like a bad connection on the board somewhere? I mean, I know I'm not using the original power supply, but the bridge rectification circuit is completely out of play and the two regulators are outputting 5 volts correctly. Guess I should probe around on the board a little bit and just try to figure out where the 5 volts on all these TTL logic is coming from. So first of all, we know the CPU is getting its good 5 volts. Is that coming from that regulator? No. This one, it's coming from that one. So even though that's an unmarked part, that's just a regular 5 volt regulator. And how about this CRTC, which has good 5 volts? It's also coming from there. So what about this chip over here, which is outputting 5 volts correctly? What is this 7805 generating its voltage for? It goes to that little tantalum there, the one I didn't replace, but that's because I knew it was on the 5 volt side and I was just like, oh, whatever, it's fine. And you know what? If this regulator is supplying the logic, there is definitely corrosion on the board right here from the battery leakage. And it's quite possible that this should be going, for instance, to here. Oh, it is now. And that's when I poked this trace. I should clean this off with the Dremel, and I bet you there's just a bad connection there, and I should have addressed that earlier. Okay, well, nothing looks broken on that trace. So let's just pick a random TTL chip like this one. And yeah, so these are getting their voltage from that regulator, and the other one is handling the CPU and the CRTC. I don't see a problem here, so I don't know what happened. Obviously, there is a trace that's eaten pretty badly right there, though. So I need to take the board off again and see where this trace that's eaten is going to on the other side of this via. Frankly, I didn't pay attention to these traces that I could see were eaten slightly because I just assumed it was all for battery and not for anything to do with the rest of the board. You know, what's really frustrating here is I definitely checked the voltage on these logic chips earlier on the video and they were fine. So this problem is new and maybe it's just been flaky the whole time. Okay, and you know what? That via that's eaten right there definitely is not the battery. It goes down to these other chips. I need to fix that trace because these chips definitely will not have any voltage on them over here. Here's what I'm gonna do to fix this. I'm gonna tin this top part of the trace here just to reinforce it. And then I'll run a bodge wire on the bottom side from where this goes over to wherever the eaten trace goes to. I'm just gonna recreate that. I was thinking of drilling a hole right through the board using this little drill bit, but then I changed my mind. I just decided to do a bodge wire. And there I just added a little offcut and I have raised it off the board slightly, like I can stick my knife under there so it's not touching that trace that is underneath it. But that's gonna give good current carrying capacity to the trace that brings down to whatever these other chips are. All right, so at this point, the output of this regulator, which is the pin on the left, should make its way to that trace, which it does, and it should go to all these various chips around the board. And it does. Now, these chips over here seem to be fed from the eaten trace that's gone now. So let's see if these have voltage, and they do. So I'm thinking that this trace here kind of worked because I poked at it and then it started working again. So that was intermittent. So most of the chips were fine, which is why when I tested a couple, they were okay. I didn't realize that the eaten trace there fed some of these chips here. And maybe that's why the board was never working properly when I powered it up. We didn't see anything happening on this chip over here. I never checked the 5 volts though. So I don't know. Let's start the whole troubleshooting process over again. Now that we know from a power perspective, we should have power everywhere. We need to see if we're getting a video signal now. Okay, here we go. 3, 2, 1. We're getting 700 milliamps. So we're getting a lot more current draw than we were before, but the video output still doesn't work. The video ROM was not installed in the board, so that could be why, but let's check these lines on this 7.4, these LS245. Okay, so it's getting good 5 volts. We're still not seeing any output on any of its pins though. What about if we power cycle the computer? Oh, there was a something there for a second. Oh, maybe. Interesting. Right, so things have definitely changed. So I'm on the direction pin on the 245, pin 1, and nothing's happening. There's nothing happening on direction. And we look at the other pin, which is output enable, and also it's not even enabling that chip. So obviously nothing is ever gonna get to the right side of this chip. It's never being turned on. But when we power cycle the computer, let's see what we get. We get a blip. We certainly do not appear to have a blip. So I'm going to change the triggering to, oh, the triggering is already on falling, and let's put it on normal mode. And let's look at the output enable signal. And I have the system off. When we turn it on, if there's any bursts of activity on output enable, we should see it. Oh, there is. Look at that. We got quite a bit. Let's redo that. So here we go, 3, 2, 1. Oh, yep, we got some activity. So let's check these other lines that are on here. Okay, 3, 2, 1. Yeah, so there's like a burst, and then the system just sort of freezes. And let's do this again. I'm on another random line on the B side there. Yeah, there's stuff happening. Okay, so I think what's going on with this, just in case you're curious, is this is it driving it low, that is floating. That's it driving it high, low, floating. So that kind of slow rise is just the output floating when the output enable is turned off. Let's check the chip select line on the CRTC now, which is this bottom pin. Yeah, I mean, there's a little burst there, so it's almost like it's writing to it, like it should be doing something. Why don't we check the sync line, 7 and 8. All right, so that's the horizontal sync, and that's doing nothing. And vertical sync is doing nothing. And now remember the read and write lines, which that's read, it's doing nothing, and write is doing nothing. I think because the system is just crashed right now. It's not actually doing anything. Light pen input, well, that's not going to do anything. And what do we have on here that we can look at? IRQ, let's look at the clock signal on pin 30. There's our clock for the video chip, 1.6 megahertz. I don't know, that seems correct, I guess. I don't know. And this is address line 0. I'm on pin 21 down the bottom corner there. There's activity. Let's go back to the address latch enable pin 30 on the CPU. So the CPU is doing stuff. It just doesn't seem to be, well, trying to talk to the RAM or video RAM. And the CRT controller didn't get initialized where it's outputting video or sync signals, that is. So this is AD0 on the CPU. We see plenty of activity. And 1, 2, 3, 4, 5, 6, 7, and this is the EA line, whatever that is. I don't know what that is. And the next one is the ALE, which we already know looks good. We already checked the reset line. Well, I have to admit, I'm a bit at a loss right now. I don't know, obviously, what this thing should be doing while it's working. And it seems to kind of run a little bit and then just kind of give up. And the odd thing is, we're not seeing the RW, the write signal, or the RD signal, the read signal from the CPU doing anything anymore. They do a little bit at the start. We see some communication over to the video circuitry and the RAM and stuff, and then that's it. There's nothing after that. But we still see the address and data lines doing stuff, so that kind of implies that some code is running in the EEPROMs. Actually, you know what we haven't done? Well, let's look at the output enable or the chip select lines for the EEPROMs. Pin 18, okay, so that's it. Well, there's definitely stuff happening there. So this is actually not tied to that RD signal, which is the memory read, or the WR signal, the write. Those obviously have to do just with the actual RAM and not the ROMs. So it's running code out of the ROMs right now. So let's check pin 20. Looks like that's just running the same speed as the clock maybe. Let's zoom in a little bit. 1 megahertz actually. But pin 20, which is one of the output enable lines, combined with pin 18, they both have to be low at the same time for it to select the ROMs. But the fact is, if we look at the output lines, I mean, we see all sorts of stuff happening here. But this, of course, is a data bus, so these signals also make their way over to the LS245, which is what I'm on there. But the other side of the LS245, I think we see nothing, because it's just floating. It's never being told to turn on, as we already established, because the output enable signal is just high all the time. And that is coming from the CPU itself, right? That was either the write signal or the RD signal that comes from the CPU. And I must say, the CPU is quite warm. Anyways, I'm thinking right now at this point, the problem we're dealing with here is either there's an issue with these EEPROMs, like the code that's on them is bad, or maybe the CPU is bad. It would be hard without a full-on logic analyzer that I could connect to, all the I/O lines in the CPU to analyze the program flow to really know what's going on. One thing I am curious about is this is only an 8-bit CPU and we have 2 ROM chips. So how are these chips addressed? I'm just going to look at all the signals that are paralleled. So these are the data lines. They are all paralleled. And then we have pin 18. Okay, that's the chip enable line. That is not paralleled. So that's coming from some other logic IC. Then address line 10 is paralleled. That signal, that's the other, that was a 1 megahertz clock signal. That's paralleled. All of these are going to be paralleled. So these ROMs, which are 4K each, are addressed separately. So the question is, which one of these chips is generating the chip select line? Okay, so this 74LSO2 at the top is generating the chip select for that one. Yeah, that pin is that chip select line, and that one is that line. Okay, and I see what's going on. I'm on both chip select lines on both EEPROMs. Notice the signal is just inverted. And I suppose that makes sense because the LSO2, I think, is just an inverter. So it's just inverting whatever chip select line. So when one chip is selected, the other one is turned off, or vice versa. Okay, so on appearance, the EEPROMs are being selected properly. They appear to be running code, but the system gets into a state where it never tries to access, except after initial burst, any of the CRT circuitry, the RAM or the CRT controller. We know the CPU read and write signals are connected directly to the LS245. That controls the direction and the output enable for it. And then the write signal also makes its way to the CRT controller and the RAM. And none of that is being turned on because the CPU is just in some kind of state where it's never trying to read and write to memory. So my only thought here is that the EEPROMs are corrupted, or maybe the CPU is bad. We could have a logic issue too, but yeah, I'm not totally sure. I think what I'm gonna do next is just dump the ROMs, and I think I'm gonna need some help disassembling these ROMs just to kind of see what the system is trying to do, so we can kind of try to get to the bottom of why it's getting stuck. Well, both ROMs have been dumped and the contents look fine. I don't see anything that's obviously wrong. Plus I did multiple verified passes on both chips and it was able to read back, consistently every single time. If you have weak drivers or other issues in an EEPROM, reading it multiple times can sometimes change the results. So you can do the verified passes. But the first chip, which was the one on the left, just looking at it, I have a bunch of stuff, which I guess is code here. But if we scroll down, we start to see what looks like strings at the bottom. Look at this, press help, press quit, online, offline, wait. And in the other chip, it's a similar story. Totally fine, verifies perfectly. And we scroll down here and we have a bunch more strings in this one. So there we go. Press a letter to dial, online, connect, originate modem, etc., etc. You see a bunch of stuff here. Press save button. There's a button on the back here. I forgot to mention that earlier. I guess saves it to some... Actually, to be honest, I don't know where it saves it. The fact there's a battery implies that there's some way for this thing to save some amount of contents to some IC. So either, I don't know, it's the static RAM or what exactly. I'm not sure. But yeah, you can see a bunch of strings here. Everything looks fine, and that's the end of the ROM. So at this point, I could use a little bit of help. I'm going to upload these ROMs to GitHub, and if anyone's good at disassembling this type of microcontroller ROM code, maybe we can try to figure out what the code is trying to do. I mean, maybe it's getting hung up because there's no battery installed. I mean, that is a possibility. Maybe it's getting hung up because I don't have the AC power supply hooked up, and it's looking for 60 hertz coming in from the transformer. I mean, there's a bunch of potential possibilities like that I'm just not sure of. But if we disassemble the code, then maybe we can try to figure out what it's trying to do when you first power on, and maybe it is just getting stuck at the very early stages of boot. It might also be possible, based on the ROM code, to identify where the CRT-C exists, if that's an I/O port. Actually, I'm not even sure this has I/O ports. Memory mapped port, and where the SRAM exists as well. And maybe we can try to initialize the video, for instance, and bypass whatever is getting hung up on. So this video was a little bit of a rough start. Obviously, we've had a few different faults we've been trying to troubleshoot here, and I was kind of going down the path of thinking it was the video section, but then the tantalum shorted, which seems to have taken out the power supply. And then even though I removed the battery, I knew about that, I just kind of made the false assumption that the traces under there were bad, and that was just going to be for the battery itself, when the reality was we suddenly lost 5 volts to the majority of the ICs on the motherboard, which clearly set me off on a few wild goose chases. So that sort of seems to be my MO lately. I'm kind of going off on tangents that aren't the right thing, but that's just how it goes when you're troubleshooting sometimes, especially something like this where you don't have schematics. I like to show that sometimes, you take wrong turns and it just doesn't always go to plan. And even though I fixed many, many things, sometimes stuff like this can stump me as well and send me off on wild goose chases, which it did. But anyhow, I feel we're at a point now where if the CPU is good and the ROMs are good, this thing should execute code and it should run normally, as far as I can tell, unless we still have logic issues. But I think it's getting hung up on waiting for something, and it's never even initializing the video, which is why we're just seeing that 800 millivolts out of the video port. So that's going to be it for this video. If you enjoyed this, then thumbs up would be appreciated. But if you didn't, you know what to do. Huge thanks to my supporters, names going on the side of the screen, and huge thanks to anyone who can help me disassemble the ROMs in this thing so we can try to figure out what's going on with it. Comment down below if you have any thoughts about any of this, and also let me know if you've ever used one of these devices. I think this thing is like an early iteration of, like, for instance, the WebTV or other internet appliances that were designed to let people get online without having to have a whole computer. Anyhow, that's it for now. Stay healthy, stay safe, and I'll see you next time. Bye.